Okay, I'm assuming I'm clicking now, so let's also do the same with ccconf record.
Recording started.
Okay, so now we are taping everything. I will try to have records of this in ccconf.org, and I will try to upload a video with this conversation. And I will put the video in Moodle. But basically, in this week, I would like to ask you guys to go to the flashcards and just browse through the words in there, like geocentric. Geo is Earth, centric is Earth in the center of the universe, is a worldview. In fact, start out a few thousands of years ago and gain popularity when Ptolemy was able to create a mathematical model supporting this view, placing the Earth not exactly in the center, but pretty much close to the center of the solar system, and having planets and the stars all going around Earth. And by doing so, observable aspects of the solar system and planets, such as prograde and retrograde motion, could be very well explained. So in this video here, in fact, I give some basic explanation of what prograde and retrograde motions are, and it's also part of a astro discussion. Okay. So browse through these words, and so heliocentric is a further development of human thought when evidence appeared indicating that Earth couldn't be placed at the center of the solar system, and Sun seems to be a more reasonable explanation to what we observed. So the heliocentric worldview is one in which the Sun is in the center. So nowadays, if you think about modern astronomy and cosmology, there is not such a thing as a center of the universe. I mean, systems, they have center part or core, like our Milky Way galaxy has a center part. In fact, we are going to learn in a few months from now that this center is occupied by a supermassive black hole, and billions and hundreds of billions of stars are then pretty much going around the galactic center. So galaxies have centers. Solar system has a somewhat a center of mass, as we could say, but the universe as a whole, the universe in large scale, does not have a center and does not have a boundary as far as we can tell or we can observe. So go through the flashcard. I always recommend that. And the astro discussion, you could perhaps Google around, or you could watch my video. It's not a long video, I think 20 minutes or so, and I explain prograde and retrograde motion. There are some extra credit available, not as much as last week that I had lots of stuff, and that's pretty much this week. So the main core material of this week is laws of motion. So let me quickly browse through the PowerPoint. See if I can get that. See if I have any question going on in. Yeah, absolutely. You were in the observatory. Yeah, we were observing Saturn. So Galileo, in fact, this is one of the points of this week class. So Galileo, using a telescope, he was not the one who invented telescope, but he was the first one who used the telescope to observe and to get a clear view of sky objects. And by doing so, he was able to note that, for instance, the moon had some features, right, with much more detail than just looking at the moon and see features. According to the religious view in those days, this is 1600 basically, Earth was in the center of the universe. God had created, the Christian church imposed that belief together with the state power. So the church was pretty much associated with the state in ruling nations. And one of the ideas was that there was here on earth things are being destroyed and decaying and going through an eternal becoming. But out there in the space, everything was perfect. Was I mean, it's above, it's the heavens. So if that is above a God, it should be perfect. It shouldn't be so chaotic, and should be regular. In fact, when the first, let's say, philosophers or astronomers in Mesopotamia and India to start observing the sky, one of the things they first saw was how regular, how harmonic, how predictable the sky was, and so the circle, and so the circle with the center, with a dot in the center, indicating perfections and harmony and everything else that should be associated with divine things, and and so the moon was this interface. The moon, I mean, if you look at the moon visually, you can see some blemishes in there, which now we know are craters and lava flow. But in those days, they placed the moon as some intermediate or some boundary between the world of decay and eternal becoming, which is here, and the world of heavens and perfection and God, which was above the moon, and the planets and their orbits and everything you see in the sky should be a representation of this harmonious motion, and shouldn't be blemishing or anything. So Galileo now, he takes the telescopes and he points the telescope towards the moon, and he see not just blemishes but features, mountains, and this is something that is weird. Second, when he observed Jupiter, he found some dots called Galilean moon. Now we call them Galilean moons. We know they are natural satellites of Jupiter. So he saw these dots going around Jupiter. Let me see if I can get that in this PowerPoint here. Oh no, there you go. No, that's chapter 2 file. Let me open the number 3. Okay, let me see. Oh, I don't have the pictures here. But yeah, Galileo, he saw basically, let me see if I can do some annotation here. So if you look at Jupiter, like this, right? So this is Jupiter. He observed, let's say today, something like that. Okay, and then next day he goes there, point the telescope towards Jupiter, and then certainly he sees Jupiter, and he sees something like this. And then he does again then the following day, and I'll put it right here. And then he sees something like this. Pa, pa. So these little dots, he claimed they were in fact satellites, like moons of Jupiter. And he was right. Today we call these dots as Galilean moons because of Galileo, and we know Jupiter has more than 60 moons going around it. And most of them are very small. They are icy types. They are not rocky type at all. But he reasoned that the relative position of these dots keep changing from night to night because these moons are in fact orbiting Jupiter, right? They are going around Jupiter. Jupiter, and then when you observe them, you see today one here, another one is there, another one is here, and then when you observe again the next day, they go in their orbit around Jupiter, and their relative position as we see them projected in the sky changes. And then he was able to say, hey, you guys keep saying in the church and in the government that everything up there in the sky goes around the Earth. And I found, and I can show you, just put your freaking eyes through the telescope. I found 4 objects, and they are here. 1, 2, 3, 4 objects that are not going around Earth. They are going around Jupiter. Therefore, the statement that all objects should go around Earth is not right, because I found 4 that contradict this argument. Isn't that cool? It's a powerful one. So another thing that Galileo also found was something interesting. You might be studying now that in the geocentric worldview, Earth is in the center, and then you have the moon going around Earth, right? And then you have, so moon first. Oh, I don't know why these things happen. Okay, moon. This is the moon, and then Mercury, and then Venus, and then where should it be? Earth. It goes the sun. So Venus, Mercury. That's the moon. Sun, and then Mars, and then Jupiter, and then Saturn. That's what they knew in those days, Saturn. So there was 1, 2, 3, 4, 5, 6. Am I missing one? Oh, it's 6 and 7 with the moon. So there was 1, 2, 3, 4, 5, 6. Oh my goodness, am I missing something? Moon, Mercury, Venus, Sun, Mars, Jupiter, Saturn. 1, 2, 3, 4, 5, 6, 7. That's correct. So 7 so-called sacred planets. Moon and the Sun was considered in those days as planets. And so according to this worldview, look at Venus. Venus is always between the Sun and Earth. So the Sun is the source of light, right? So you have the Sun as a source of light, and here's the Earth where we live. And according to this worldview, Venus was always here, always. Now, Venus, they knew Venus was, I don't know why this software does this. Venus was a circle, a sphere, in fact. Okay. So any sphere, Harry, if you go with a sphere like an orange, or like a ball, like a basketball, and you place between your eyes and a light source, like a background light source, could be a lamp, could be something, and you look towards the ball or the apple or the that you're holding, one thing you're going to see when you look at it, this sphere will always show the following phases, and the phases are crescent, either waxing or waning. So again, any sphere that happens to be between you, observer, and a light of source, and a source of light, like the sun, will be perceived as in a crescent phase. Okay, got that one? So, which means the moon should, Venus should always be, according to the geocentric worldview, should always be in a waning phase, in a crescent phase, a waning or waxing. And so when Galileo put his telescope there, voila, what did he saw? He saw that sometimes Venus was in a gibbous phase. Gibbous phase. So gibbous phase is more than crescent, right? So this is a crescent part. So Venus is more lit than 50% of its hemisphere facing Earth. So it's in a gibbous phase. Now, to be in a gibbous phase, what requires? Well, requires that your object is here. So here's your eyes as an observer on Earth. I can take this away. I don't need this Venus here, right? So we don't need there. And here's the sun, right there, the sun. And if Venus happened to be here, in respect to the sun, we are going to see it as in a gibbous phase. If Venus happened to be here, then we see Venus as in a crescent phase. Bad crescent, mine. Oops, there you go. Like, oh, geez, I cannot write a crescent. There you go, crescent phase. Kind of a bad one. You got that one? Let's see if you have any question there. Okay. So Galileo said, hey, I found Venus. And Venus goes in gibbous, which means Venus is not going around Earth. Venus is going around the sun. Venus is, in fact, going around the sun. So we have the sun right here, Venus. Venus go around the sun, doesn't go around the Earth. So Tycho Brahe was an observer and astronomer. He had a worldview that placed Earth in the center of the solar system, and Mercury and Venus going around the sun, and the sun itself going around Earth, in order to accommodate what Galileo observed, and still keeping Earth in the center of the solar system. But, this geocentric worldview came to be discarded when more and more evidence appeared, when Copernicus not only brought his heliocentric worldview into play, providing mathematic basis for it, and especially when Kepler's law came to be presented by Kepler. And Kepler's law are also some important, crucial aspects of this section. And it says that any object, as it gravitates another one, like here you have a planet. You have a planet going around the sun. So it doesn't go in a circular orbit like Copernicus would say, but it goes in what's so-called elliptical orbit. Elliptical orbit. So a circle is an ellipse that is not flattened. It's kind of a perfect ellipse, right? Not flattened at all. And the planets don't go in circular orbit around the sun, but they go in elliptical orbit. Not as flattened as the one I'm showing, but kind of somewhat flattened. And the sun is not in the center, but a little bit off the center, like it's being shown here. See that? So this distance here is bigger than this distance here, right? The sun is not exactly in the center. So elliptical orbit is the orbit of all planets around the sun. The moon exerts and undergo an elliptical orbit around Earth, and all the satellites undergo elliptical orbits around their parent planets. Some of these ellipses are very eccentric, and it's like Pluto, and Pluto was considered a planet. Pluto's orbit was the most eccentric of them all. So, but now Pluto is not a planet anymore, but still has an eccentric orbit. And the first law of Kepler is this. Kepler, he worked hard with data. In fact, most of it collected by Tycho Brahe, and he inherited his data, and he used it to develop his mathematical approach to planetary orbit. The second law of Kepler is kind of a funny. It goes like this. So if you take the planet and you draw a line from the planet to the sun, like I'm doing here, right? And you take that line, and as the planet, I don't know why it does that. And as the planet, see, it creates this box. I have to learn how to use this thing. And as the planet orbits the sun, this line will fill an area that has a certain value, okay? Now let's say you were able to measure this time. So the time that takes the planet to go from point A to point B. And I'm going TAB. And here we have a point C and D, right? In a further away orbit, part of the orbit. Now, if this time is calculated and you measure the time to be the same as it takes the planet going from C to D, so for this to happen, the planet has to go much slower when it's further out, right? Because here the planet has to cover in a certain amount of time a path that is bigger than it is when it's further out. So which means when the planet's further out, it has to go slower. It takes longer time. So what Kepler's second law says is that the line connecting the planet to the sun, to the focus, will sweep out an equal area. So, which means the green area right here is equal to the red area right there, which is equal to the blue area right here, as long as the time the planet goes from E to F is the same. Right? Equal areas, equal amount of time. What's the consequence of this law? Well, the consequence of this law is that when the planets are closer to the sun, going in a position that we call perihelion. Helium is the sun. Peri is close to. When the planets are closer to the sun in the perihelion, they have to go a little bit faster than they go when they are further out in the aphelion. Aphelion. Helium. Okay? So that's the second law of Kepler. And the third law is the equal is that if you are able to determine how long it takes your planet to complete one complete turn around the star sun in respect to the stars in the very far background, and this is the so-called sidereal period, which is the year, right? Is the year, 365 days and a quarter, is how long Earth to complete one turn around the sun in respect to the stars that are in the far background. Okay, so that's the sidereal year. So this sidereal year, if you square it, it's going to be equal to the semi-major axis, which means if you take, see, I can't have these things working. I don't understand why. So if you take the semi-major axis, which is half of this distance here, so according to Kepler, the square of this yearly turn, which is a number, is equal to the third power of semi-major axis, which is the half of, which is the average distance of the planet to the sun, and that is so-called Kepler's law. One of the consequences of this law is that when the planet is further out, which means when A is bigger because it's further out with respect to the sun, the time it takes the planet to complete the turn also increases. So which means it takes much longer to go around and complete an entire revolution around the sun. So the further the planet is, the slower it is. So the longer it takes to complete one turn around the sun. So those three laws of Kepler's were later on explained and proved by Newton. And Newton not only explained this law, and in fact he had to develop calculus in order to explain the second law of Kepler, but he was able to create a model which we call the universal law of gravity. And that is, if you have two objects with their masses, right, calculated, these two objects, they attract each other with a force that is equal to a constant times the product of their masses divided by the distance of these objects, in the case of spheres, from center to center to the second power. So if you think about the sun and the planets, so the force in which the sun attracts the planets is proportional to the mass of the sun times the mass of the planet times a constant, that's a very small number, divided by the distance squared. So, and that's Newton's basic laws of the three laws of motion that build up this universal law of gravity. Okay. Let me see. And this pretty much this cubes cube of semi-major. Yes. Didn't they put that? Where is it? T2 is equal A3. Didn't I put that? What is it? No, it's, oh, there you go. So the period square is equal to the cube, the third power of the semi-major axis. You're right. Okay. Yes. Yeah. Well, the retrograde motion is a funny thing. You are right. You are touching the exact point. Because if you take, for instance, take a white board here. So if you take, for instance, the sun, and you have a planet let's say Earth, right? Earth is right here. Earth orbit, and they have another planet, Mars, right there. And very far away, right there, we have stars, right? A bunch of stars. Now, let's say Mars is here. I don't know why this happened. I have to learn how to use this software. Why keep moving? Do I have to start all over? I don't know. Now my orbits are all crazy. Okay, that is Sun and Earth. And then I... Come on, Harry, you're the one who... Hadi, you're the one who studied Python. You should know computer. Can you help me out here? What's going on? Look. Man. Let's start all over. Right here. I will be careful. I will try not to cross lines. But here's the Sun. Here's planet Earth orbit. Here's planet Mars orbit. and you have a bunch of stars right there. Okay? And so you place Mars, I'm not going to cross now. You place Mars here, and you place Earth right there. Okay? Now, from Earth, you look and observe Mars, right? And you see Mars in projection right against the star, this star. Oh, it happened again. Right against this star right here, right? Now, a couple of weeks later, Earth has moved this much, but Mars, because as you said, Kepler's third law, moves just a little bit forward. And then when you observe that Mars again, you're going to see it probably still going a little bit further, prograding, but it's going to take a moment when Earth is here and Mars is there, that you're going to observe Mars, and you're going to see Mars going from up here down there. So Mars is retrograding. The normal direction of motion would be from, in respect to the stars, we would be able to see Mars going always from west to east in respect to the stars. But sometimes this normal motion retrogrades, and we call retrogradation. And then the planet, as we see, appears to go the other way, the other regular way, which is from east to west. Now, you should note this prograde and retrograde motion, as I show in the video that I upload. It's not detectable in time scales of few hours. It's something that requires detailed observations from night to night. And then in time scale of a few weeks, you can detect this retrograde motion of a planet in respect to the background. So you were right. It is Kepler's third law is very important to understand that. Voila! Yes, there you go. But you know what? I mean, now we have this concept of, center, the sun in the center. We are all educated. We are all happy with that. But going back to the old geocentric worldview with Earth in the center, do you know this prograde and retrograde motion, the way they explain? Because they put it, what they did, they had Earth in the center, right? And here is, let's say, Jupiter. And they say, okay, Jupiter doesn't go in a circular orbit around Earth, but Jupiter goes in a funny orbit, which is this. Let's say Jupiter is not orbiting Earth. Its orbit would be a circle with a center in here, right? So what they say is this: well, Jupiter goes around in a circular orbit around a point, but this point in its turn orbits around Earth in a path that we call the deferent. So which means Jupiter would go around Earth, according to the geocentric worldview, something like this. Progrades, retrogrades. Progrades. I'm going to slap the lady. Retrograde. And I'm not going to keep going. But you got the picture. So the planet prograde and then retrograde. And then progrades and retrograde. Because the center of the planet orbit around the geocentric is the one going around Earth. Now, how this match observations so well? Well, because it happened in their worldview when Jupiter is here, which means it's closer to Earth, it should appear brighter, and it did. And when the planet is further out in the prograde motion, it should appear dimmer, and it did. So geocentric worldview, although is a model that does not fit reality, it could fit observations very well, to the point that even when the heliocentric worldview came up, it didn't predict planet position as well as the geocentric worldview. It took a time for the geocentric to be completely discarded. So this is one of the perks of science, right? Sometimes you have two models. They predict observations and they match observations quite well. You have to keep using them up to the point that something comes up and then forces you to put your good model, the one you loved a lot, in the garbage. And so Galileo Galilei was the one who helped to bring evidence, putting down the geocentric worldview with his observations of Jupiter moons, the Galilean moons, with his observations of Venus in Gibbous phase, with his observations of moons craters, showing that the sun was not a god lacking blemishes. The sun has sunspots, have all kind of things going on. So he was able to come up with lots of evidence indicating the Earth was not in the center. And then eventually, the geocentric worldview, no matter how well it fit observations, it didn't fit reality, right? So reality is always the last word in this chain of research. And so, do you have any question more to ask? I'm going to stop taping now. Let me see, I go here in tools.
Recording stopped.
And I also go in here.